Okay, so let's just, oh, what happened to this? I wanted the other one. So let's just recap very quickly what we did last time. We looked at tracking two quantities associated with the bug going around in a circle on the fan. And we came up with this graph. So what I want you to do is recall with the person next to you, what were the two quantities that we were tracking together, or looking at how they changed together? What two quantities specifically we were looking at? Okay, so recall that with the person next to you. So what quantity do we consider the input, or what were we looking at in terms of the input quantity here? What's that? Not quite. Yeah, we were looking at angle, right? We were looking at angle as the input, and I've got that right here. So I hope this works better than last time. Okay, so here's what we got for input. The angle swept counterclockwise from the 3 o'clock position. That was our input quantity. And what exactly is the output quantity that we're looking at here? Okay? So it was a distance. Was it a vertical distance or a horizontal distance? Vertical distance. Oh, it's working better. Thank you. Vertical distance. Where relative to that horizontal diameter? What was that? Yeah, so we want to make sure that we really specify. We're going to say above, so that naturally we'll get this distinction between positive and negative values of vertical distance. So vertical distance above the horizontal diameter. And in the end, we said, let's make it universal for all circles, so that when it gets to the top, it's 1 above, and when it's below, it's -1. And so 1 what? So what do we? If we use 1, we're measuring this vertical distance in terms of what? What's that? Radians is angle. So radius lengths. And by doing it, by measuring in radius lengths, really we just track the vertical distance for a point on all circles. Whether the circle has radius of 100 meters or ½ an inch. Every circle we can measure then in radius lengths, and that way we have a generic way to represent every circle with just one function. Okay? And then we saw how the graph came about, and this is tracking the vertical distance. Vertical distance increases up to 1 full radius length at the top, then back down to 0. Then the bug gets to the bottom, it's 1 full radius length below, and then back to 0. So when we use those two quantities, we said that's a universal function, and we called that function, what did we call it? That was sine. Okay, really important that you just have the input and output of sine, input and output, just nailed down, because that's so really knowing without hesitation, without with full confidence, knowing what the input and output of sine is means you really understand what the sine is. Okay, it all comes down to what goes in and what does the sine give you. Okay, and so we'll keep reviewing that. So now just quickly here, Now let's do the same thing, but we'll track, instead of tracking vertical distance, we're going to track horizontal distance. Oh, I want it to be there. All right, so now we want our output quantity to be, instead of the vertical distance above horizontal diameter, it's going to be horizontal distance right of vertical diameter. And again, we'll just go straight to radius lengths here. So before we did it in feet, and then we said generalized to radius lengths. We'll just start right here in radius lengths. So at an angle of 0, what is the horizontal distance to the right of the vertical diameter in radius lengths? Starts at 1, right? So here on the vertical axis of this graph, we're plotting horizontal distance to the right on the circle. So this is a little more confusing. So the up and down on this graph that we're going to plot here is corresponding to horizontal distance right and left of the vertical diameter. So at an angle of 0, it's going to start at a full 1 radius length to the right. Okay, in this first quarter circle, as the angle goes from 0 to pi over 2, what will the horizontal distance right of the vertical diameter do? He said get closer to 0. So it starts at what value? 1, and will go to? It'll go to 0 because the bug will head back to the vertical diameter until it's at 0. So if we were to graph that, if we let that angle change, there it is. Okay? So what angle are we at now? Pi over 2 radians. 1/4 circle. 1/4 circle, pi over 2 radians. Okay, in the next quarter circle, or the second quadrant, when we go from pi over 2 to pi, what will the horizontal distance right of the vertical diameter, I should have put here, in what? What are we measuring that in? Radius lengths. What will that quantity do as the angle goes from pi over 2 to pi? Start at 0 and decrease to? Down to -1. So again, vertically here on this graph, up and down means left and right in the circle, right? The output we're graphing this way is representing how far left or right of the vertical diameter we are. Okay, next quarter circle, that quantity of horizontal distance will change from what to what? He wants -1 to 0. Agree with that? Yep. Because it's 1 radius length to the left, now it's coming back towards the vertical diameter until it reaches the vertical diameter. So now it's 0 radius lengths to the right. So it basically moved from out to the far left back to the middle position. So that's -1 radius length to 0. What angle are we at now? 2 pi. We make it 2 pi radians? Actually 3/4 of that, right? We didn't make it all the way around yet. So it would be 1.5 and 1.5 pi. Okay, in the last quarter circle, as we finish up one rotation, the horizontal distance, he says, going from 0 to 1. Agree with that? Now it's at 0, and then it's going out to 1 radius length. Back to our starting position of 1 radius length to the right of the vertical diameter. Okay, again, now this is universal for any circle because we used radius lengths. We used radius lengths to the left and right. And so this will work for any circle, so it's a special function. We'll call this one h. Some of you know what this one is. This is our cosine function. Okay, so again, this is the key. What's the input into cosine? What's the output into cosine? if you really, without hesitation, fully confidently know what the input and output into cosine is, then you understand what cosine is. You understand what it does, right? It's a function. Okay, so practice. Oh, that's not going to work. So practice with a person next to you. So if h of theta is cosine, that's too small. If h of theta is cosine theta, describe specifically and completely what the input quantity is and what the output quantity is. Go. Okay, what's the input into cosine theta? What is the input into cosine theta? The radius lengths from the horizontal diameter. The input? That's not the input into cosine. Yeah. Okay, and what does it mean? So what theta is it? Right. So we got what angle? So relative to the circle, we could name dozens of angles. Which angle are we talking about? Okay, that's just describing what radians is. So what angle are we talking about? Is it this angle? That's an angle. I can measure it in radians. Is it an angle like that? Okay, so it's the angle swept what direction? Counterclockwise from the 3 o'clock position. It's the angle swept counterclockwise with initial side at the 3 o'clock position. Okay, that's the input into cosine.
Why is it the 3 o'clock position?
That's convention. Yeah, that's just convention. Okay, and then what about the output of cosine? What would the output of cosine be? The input's the angle swept counterclockwise from 3 o'clock. Output is? Horizontal distance from the vertical diameter. Okay, we missed one little detail in there that's important.
To the right.
Horizontal distance to the right of the vertical diameter. And one more thing. What's that? In radius lengths. In radius lengths. You got to practice that. Memorize it. Memorize the idea. Okay. So you got to just keep practicing that. All right. So if we've got these quantities of sine, which means vertical distance above the horizontal diameter, and cosine means the horizontal distance to the right of the vertical diameter, we could think about this in the coordinate plane. Think of the vertical diameter as the axis and the horizontal diameter as the axes. Okay, good enough right there. Okay, so what would be another way we could describe, say, the horizontal distance to the right of the vertical diameter what would be another way to express that? Isn't that length right there? What's a simpler way to express that right there? Okay, it's cosine theta, that's right. But according to looking this like in the coordinate plane, right? The coordinate plane. Here's your vertical axis, here's your horizontal axis. What is this distance? What is this distance right here? Someone asked, is it x? Is it x? What is the x coordinate of a point? Is x coordinate the distance to the right of the y-axis? Is that what x is? Yeah, that's what it is. X is how far you go right if positive or how far you go left if negative. Right? So isn't this just the x coordinate of this point right here? Where the bug ended up? Okay, and what about vertical distance? That's easy now, right? That's just the y. So, if this is our point, say on the fan blade's 2.6. So if this is the point 2.6 feet, comma 0 feet, right? That would be the coordinates of that point in feet. We have a way of writing now the coordinates of the bug for any angle that the bug turns. So how would we do that? How can we express, so let's say the bug has turned an angle of theta. Okay, so what is the x coordinate in terms of theta? Is it cosine theta? So what is the output of cosine theta? It gives the horizontal distance to the right of the vertical diameter in what? Radius lengths, right? This is radius lengths. So is that the coordinate of the x coordinate of the bug? He wants to multiply it by the radius. All right, let's estimate this in radians. Let's estimate this angle and actually get some values. So if you were to estimate this value of theta in radians, what would you just toss a number that's close out? Could you do it? He said 4.7. Someone said somewhere between 4 and 5. Where is 3? Is 3 before or after the horizontal diameter? 3. 3 is about here, right? Because halfway around is about 3.1, about. So are we before or after 4 here? Looks like we're after, maybe 4. I don't know. 4 is around here somewhere. Radians is the openness or the angle that subtends that many of radius lengths. So, estimating theta. All right, 4.5 is great. So we'll go with 4.5. So let's find the cosine in your calculator. Find the cosine of 4.5 and find the sine of 4.5. Make sure your calculator is set to radians because this 4.5, it's radians, right? It's how many radius lengths we are. So let's just get these values. Cosine 4.5 and sine 4.5.
For cosine, it's negative 0.21.
Okay?
And then for sine, it's negative 0.9.
So let's change it to, based on where the bug is, I think it's probably closer to about 4.3. So let's do 4.3 instead. So our angle is 4.3. Tell me again.
So cosine is negative 0.4.
Negative 0.4.
Yeah. And then sine's negative 0.92.
Negative 0.92. So did you all get that? Are you all able to get that? So now we got to make sense of those numbers relative to the bug right here. So just take a minute to discuss with the person next to you. Why do those numbers make sense relative to the position of the bug? Negative 0.4 and negative 0.92. Go. Why do those numbers make sense? What do they mean? Okay, what do we come up with? So, who can say what the meaning of the number negative 0.4 is? Why does it make sense in this picture? What's the meaning of that? Yeah?
The distance from the vertical diameter.
Okay, the distance from the vertical diameter. Why is it, how do you see there that it's negative 0.4?
Because it's to the left.
Negative means to the left. What about the 0.4? If it's a number of radius lengths, then it's less than half of radius length. Is that what you see there? Yeah, because how many? It would be this of a full radius length. So less than halfway of a full radius out to the left, negative. So it makes sense. What about the negative 0.92? What does the negative mean? Below the horizontal diameter rather than above. And then what about the 0.92? Is the bug almost a whole radius length down below the horizontal diameter?
Yeah.
Yeah, because the bug is down this far, right? It's down this far, or where I've written the y-coordinate, which is about 90% of a full radius length down below. So, are those the coordinates of the bug? Well, it depends. So what were we going to say?
I think you have to multiply 4.3 by that value to get the.
If I tell you the coordinates of this point right here are 2.60, then are those the coordinates of the bug? No, because I'm now measuring everything in feet. So what I'm doing is measuring in feet. So if that's the number of radius lengths, and we know each radius is 2.6 feet, then to get x and y, we're going to do? What's that? Yeah, so if this is how many radius lengths, then we're going to multiply it by the radius. So the x-coordinate of this point will be 2.6 times the cosine 4.3, and the y-coordinate will be 2.6 times sine of 4.3. So let's find approximations for those values and then verify that they make sense. What do we get for the x-coordinate? I'm guessing that's the y-coordinate. Negative 2.38? Okay, what about the x-coordinate? Okay, so negative 1 is less than halfway out to a full radius of 2.6 feet. It's actually 0.4 of the way. And then the 2.38, does that number make sense? It's almost, what? Almost a full radius length down below, and that's where we see the bug is. Okay, any questions? Really important idea here. Why is this important? Because now using sine and cosine and knowing the radius of the circle, we can pinpoint the location of any point on the circle, knowing what angle and knowing what the radius of the circle is. Yeah. Yeah. So that's kind of the foundational thing about what cosine and sine are. They allow you to track any point on the circle given the angle and given the radius of that circle. Okay, so over here, the bug is in negative x territory and negative y territory, right? So I should put negatives here, right? Shouldn't I put negatives here? Why not? So should we put negatives out here since those x and y coordinates are negative? Exactly. So how do we define cosine? It was the distance to the right. So by defining it as distance to the right, automatically when you're left, it comes out negative. It comes out negative. And automatically with sine, we defined it as distance above. So whenever you're below, automatically the sign comes out negative. So it's built in. Okay? It's built in. Okay. Anybody have a question about this? Critically important. So let's I gotta be able to see the track here. Does that show up? The track? You gotta have the track. You gotta be able to see the track. Oh, barely. Well, it makes it look like someone ran over him. Let's try green. There we go. That's better. You see that? Yeah, that's good. Okay. Neon green track, right? To match the hot neon green shoes everyone's wearing. Okay, so he's going to start over here. We're just going to consider this semicircle that he runs around this circular end of the track. Okay? So our runner is going to run 18 meters. So no calculators for this. We'll pull out the calculator later. No calculators. The runner runs 18 meters around the circular path of the track. Okay, so without a calculator, how would you express the angle of rotation that the runner has swept here by running 18 meters? What's the angle the runner has swept by running 18 meters? So I'm just going to write out these questions and you can work on them. So, what's the angle, corresponding angle for the 18 meter, okay? How many radius lengths is the runner? Right of a vertical diameter above horizontal diameter, and then how many meters? Same question, how many meters? No calculator, so everything's you're writing out longhand expressions. So take a minute or two to work on this. You can compare with the person next to you. So the first question is, what's the angle corresponding to running these 18 meters? How many radius lengths is the runner to the right of the vertical diameter and above the horizontal diameter? And then the next question, how many meters is the runner to the right of the vertical diameter and above the horizontal diameter. Okay, go. So don't just wait for someone else to or myself to say the answer. Think about this. You got to know this. This sets the stage for the rest of the module. Really important. Can you ask a question? If I lose you, ask a question. And then if you're confident about 1 through 3, then find decimal approximation for the coordinates of the runner. Yeah, you need a calculator for that, number 4. Okay. What's the angle associated with this runner going 18 meters around the arc? What's the angle associated with that? He's offered up 18 divided by 31.83. If we want the angle, then we want the number of radius lengths that is, right? If we can get the number of radius lengths that he's run, that's the same as the angle in radians. So how would you get how many radius lengths 18 is if the radius is 31.83? Yeah, you're just going to take, it's going to be a number less than 1. It's going to be that.
How come you have divided by 360?
Because radians is a number of radius lengths. How many radius lengths did he run? How many radius lengths did he run if he ran 18 meters? Has nothing to do with 360. How many radius lengths did he go? More or less than 1 radius length? Less, because 1 radius length is 31. So how would you find what fraction of a radius length he's run? Does it make sense? You see, it has nothing to do with degrees. Okay, so how many radius lengths is the runner right of the vertical diameter? In other words, how many radius lengths is the runner to the right of the vertical diameter? How could we express that? What is it? It's going to be the cosine of 18 over 31.83. That's what cosine gives us. It gives us the number of radius lengths to the right of the vertical diameter. Okay, how about above the horizontal diameter, or this right here? That's going to be our sine. Okay, let's estimate those. What would you estimate cosine of 18 over 31.83 to be? What would you estimate it to be? What's that? Something like 29 or something like 0.9 cosine. Like 0.9. It's the number of radius lengths. So maybe this is around 0.9 as a guess. Do you see that? And then what about the sine? Something about? Yeah, something about 0.5, right? So in terms of radius lengths, is about half a radius length. Here's a full radius length above. So he's about halfway there. Okay, those are just loose estimations just to make sure we understand. Okay, what about how many meters? So now how many meters is this? How could we get exactly how many meters that is? Yeah, if it's this many radius lengths, how do we get meters? Yeah, we're going to take 31.83 and multiply by the cosine of 31.83. And then what about in meters, the y-coordinate in meters? It's going to be the 30. We'll take the number of radius lengths, which is sine. And we'll multiply it by the length of one radius. Okay, so let's get decimal approximations for those numbers. So this is the coordinates of the runner in meters. Anyone got a decimal approximation? 29 something? 26.7? 26.9 meters to the right, and how far up? 17.1 meters up. Do the numbers make sense? If the radius is 31 or 32, almost a full radius length, or 27 meters over, and 17 meters are about a little more than half of a radius length up. Anybody have a question?
Did you go over estimating without using
The 0.9 and 0.5?
Yeah.
So just saying, if this is a full radius length, we know the cosine will give us how many radius lengths to the right. This is how far to the right he is. So we just said about 0.9, see?
So you kind of have to graph it, yes.
Yeah, well, I'm just looking at how far to the right is he in radius lengths. If this is one radius length here, how far to the right is he?
Okay,
About 0.9, right? And then how far, if this is one radius length up to there, then how far up is he?
about half.
About halfway. So that's 0.5. You see? Other questions? Okay, let's try top hat on this. So we'll do 2 questions at a time. There'll be the first 2, and then we'll go over them, and then the second 2. Unless there's questions on this.